Now next topic we will be discussing is Bayes theorem, right? So Bayes theorem tells about reverse probability, right? Given that event B has occurred, what is probability that it came from A, right? Suppose I have an event A, right, and B has occurred. So B came after A, and what is the probability that B came after A, right? So this will be given as probability of A index given B will be probability of A index, right? By probability of B given A index whole by probability of B or probability of A1 multiply probability of B given A1 plus probability of AN multiply probability of B given event AN is occurred, right? So we will solve a question on this. This is Bayes theorem, right? So given item is defective, probability that it came from machine A will be probability of getting the item from machine A, right? Given that the item is defective, it is probability of A into probability of item is defective given A by probability that item is defective, right? So it will be, this is the values you will put and you will get the answer, right? Now properties of conditional probability. So first property is probability of A given E will be from 0 to 1, right? Because A intersection E is subset of E, right? So probability of this will be event A intersection E will be less than equal to probability of that event occurred, right? Second property is sample space maps to 1, right? So probability of getting sample space from event, that event will be 1, right? Because getting sample space and intersection of that event, I will get E, right? And probability of sample space intersection E by probability of that event will be simply 1 by 1. That is probability of E by probability of event E, right? Now, when A is subset of B, so probability of B given A will be simply probability of A by probability of A, because A intersection B will be simply subset of, so this intersection will be simply A, right? This will give me 1. Now both if are mutually exclusive, that is both are independent event, so no intersection, that means probability will be 0 if A and B are mutually exclusive. Now my question is suppose there are 4% men, I am writing from there. Suppose there is 4% men and 1% women taller than 1.8 meter, and out of 100, 60% people are women and 40% are men, right? So find probability that the person is woman given she is taller than 1.8 meter, right? So let's assume there are 1000 students, 600 students are women, 400 are men, right? Now women having height greater than 1.8 meter will be 1%. So 1 by 600 into 100 will be, sorry, 1%, 1 by 100 into 600 will be 6 women, and men will be 4% are men. So 4 by 100 into 600 into 400 will be 16 men. So number of people that are taller than 1.8 meter will be 22, right? And out of them 6 are women, so it will be 6 by 22. Probability of women which is taller than 1.8 meter, right? So this will be the answer. Now let's discuss about independent events. Two events A and B are called independent if knowing one has occurred gives no information about other. Independent events are two events, suppose A and B, both has occurred but they don't have information about each other, right? So this will be probability of A intersection B will be probability of A multiply probability of B. And if A and B are mutually exclusive, right? Outcomes, mutually exclusive events are outcomes that cannot happen simultaneously in a single trial. So this will be equal to 0 because there is no intersection, right? Now here are some questions. Suppose I have to prove probability of A intersection A complement intersection B complement will be probability of A complement into probability of B complement. So this I can write it as 1 minus probability of A union B, and this I can write it as 1 minus probability of A plus probability of B minus probability of A into probability of B. So this will be written as 1 minus probability of A multiply 1 minus probability of B, which can be written as probability of A complement into probability of B complement. Similarly, if I have to prove probability of A complement intersection, these are possible only if A and B are independent events. Only if A and B are independent events, right? This I can write, this I have to prove as probability of A complement into probability of B. So this I can write it as, this is what? A, B, right? So I don't want A, I don't want A, I want everything, but it should have intersection with B. So I want this region, right? This is the region I want. So I can write it as probability of B minus probability of A intersection B. This I can write it as probability of A into probability of B. So this I can write it as probability of B into probability of A complement, right? Now pairwise versus mutually independent events. So for 3 events, let's say there are 3 events A, B and C, and these are pairwise pairwise independent. So it means each pair is independent. So it means probability of A intersection B will be probability of A into probability of B. Probability of B intersection C will be probability of B into probability of C, and probability of C intersection A will be probability of C into probability of A. Right. Now mutually independent means probability of A intersection B intersection C will be probability of A into probability of B into probability of C. Right. Now conditional probability with mutually exclusive events. If A, B, C are mutually exclusive and suppose A, E is any event, right? So probability of A union B union C given event E has happened will be given as probability of A intersection E union B intersection E union C intersection E divided by probability of E. Right. So this I can write it as probability of A given E has happened, probability of B given E has happened, plus probability of C given event E has happened. Right. Now there is a question. I am erasing this as I have to solve a question. So I am erasing this thing. Right. So suppose there is a question. If there is there is a person called A who wants to hit the target, and there is a person B who also wants to hit the target, right? So probability that that person will hit is 1 by 4, and probability that person B will hit is 2 by 5, and the probability that target is hit if both fire will be given as, now since target is hit means either A has happened or B has happened, right? So probability of A union B will be given as probability of A plus probability of B minus probability of A into probability of B, as A and B are independent events, right? A and B are independent since they fire separately, right? And now you can easily find it, right? Now there are three horses A, B and C who race twice, right? So probability that horse A wins is 1 by 2. Probability that horse B wins is 1 by 3. And probability that horse C wins is 1 by 6. So find sample space and probabilities, right? So since there are three horses and either they can win or lose, the sample space will be 3 to the power 2, that is 9. So suppose the outcomes are horse A and A, B and B, C and C, A with B, A with C, right? B with A, C with A, B with C and C with B, right? 9 cases. And now probability, right? So probability of A winning is 1 by 2. So probability of A winning is 1 by 2, and these are independent events, right? Simultaneous events, A and A are running together, so I will multiply, and this is also probability of horse B winning is 1 by 3, and again 1 by 3, and then probability of C winning is 1 by 6, so I will multiply it with 1 by 6. Now probability of horse winning A is 1 by 2, and probability of B winning is 1 by 3, so I will multiply. Since this is a simultaneous event, it is happening at same time. Similarly, I will also find this by multiplying them. So this is how I will get my probabilities of these outcomes, right? So this is all for this video. We will discuss next topic in next video.